Syzygy, episode 115, Zevatron in the Void. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, and I am sitting around the round table in the office of Dr. Emily Brunsden. Emily, how you doing? It's
Hello.
been a while.
Yes, it has been a while. There's been a bit of life that's gotten in the way, I think, for both of us.
Life has a way of doing that. I'm not going to... Let's not go into too much detail about exactly what life has been doing for the last couple of weeks, but suffice to say, you've had a fun time. It's been an entertaining couple of weeks.
It's been different.
Yeah.
Yeah.
Anytime that insurance companies get involved, that's a story. But look, that's for another podcast entirely. We're talking about astronomy today. And today we're going to be talking about something which is kind of weird. Something really weird has happened. Mm-hmm. And in fact, as far as I can tell, it's like there was a really, really, really weird thing that happened many years ago that made astronomers and particle physicists go, oh my God, what was that? And then just recently, there's been another one. And there's not many things in the universe, in the world of science, in astronomy, where every several decades you have to sort of sit up and pay attention and go, wait, it's happened again. I'm talking about really, really high energy particles from space, but like one of them. Like normally particles come in large quantities. You know, a beam of light is loads and loads of photons, or in the Large Hadron Collider, you've got huge numbers of particles in a big bunch slamming into each other. No, this is one. We're talking like astronomers have seen one really ridiculously energetic particle and made them go, what the hell was that? Emily, what's going on? What's been seen? Who saw this? Where even are we?
So this was something that really struck me, was that these events are so special and so unique that these particles get individual names.
Yeah, like when does that happen? And we're not talking like, oh, it was an electron or it was a proton or it was a photon. No, actual names for the particles themselves.
Yeah.
So what's this one?
This one's called Amaterasu. I'm going to pronounce that as if it rhymes with tiramisu because that sounds like a good
Although I
approach.
think you're getting your cultures crossed there. Tiramisu from the Italian, I think, whereas this is a Japanese word. But whatever.
Yeah, whatever. The word itself means sun goddess from Japanese mythology. Mm-hmm. But the particle holds the illustrious, I think, title of the third highest energy cosmic ray ever to be detected from space.
Right, the third highest. I had seen second highest. So obviously I missed something along the way.
You missed one.
Missed one along the way. Okay. So, I mean, off the bat, right, this particle not only has a name, but when you give the name the sun goddess to a particle, something's happened, right? Yeah. You got to do something to earn that as a particle. This is not your common or garden variety photon or whatever that we've just spotted here. So why? What's happened?
Yes, well, it's important that we distinguish that although that particle is the third highest energy cosmic ray that we've ever measured, that's brilliant, that's wonderful. Actually, that's old news.
Okay.
Yeah, so that we actually measured this particle back in 2021.
Right, okay, so this is a couple of years.
So a couple of years ago. What the new thing is that we're going to be covering today about this particle is that it's come from nowhere.
So not only is it bad enough that it's like, wow, like look at that. That's amazing. That's the highest or third highest energy thing that we've seen in like a really long time, ever. But if we look at where it comes from, nothing.
Yeah.
Okay.
Absolutely nothing.
So we need to unpack.
Absolutely, yeah.
Where do we begin?
So this is a paper that came out just in the last month. So November 23. It's come out from a collaborative group who work on what's called the Aperture Telescope in Utah. And so this is a really interesting, specifically designed telescope for looking at cosmic rays, and we'll go into sort of how it does that and what that means. But what they've been able to do is, after the detection of this high energy particle, first of all, they've been able to backtrack and then say, well, where did that come from in the sky? And you have to do a kind of bit of quite complicated modelling, but once you sort of get your grips around all that, they've been able to determine that it's come from basically a galactic void.
Right.
So it's come from a place where there's nothing.
Which is interesting, if somewhat perplexing and a little bit inconvenient. You know,
Yeah.
if there was something really obvious there, like, oh, I know, great honking supermassive black hole, or something else, I don't know, then you could go, right, that makes sense.
Yeah.
Could imagine where that one's come from, but nothing.
Yeah, because this is
That's
the problem.
odd.
High energy particle, like
Yeah.
one of the highest energy particles that we've ever detected, needs a pretty energetic event to generate such a high energy particle, right? It
Yeah.
kind of follows.
Yeah.
Yet there's just empty space.
All right. So there's a few things there that we need to cover. First of all, when we talk about high energy particles, like what are we talking about here? Like how big is this energy?
Yeah,
How
yeah.
impressive is this? Like third highest ever? Yeah, sure. But I mean, maybe that's like on a scale of tiny to ever so slightly not tiny.
Mm-hmm.
How big is this energy?
Well, okay, so let's get an energy scales. We're gonna contextualize this with some wonderful numbers. So this particular particle, the Amaterasu particle, is believed to be around about, as the energy is not exactly measured, but it's at least as much as 240 exa electron volts.
Exa electron volts. Okay, so an electron volt is very, very, very small, right? That's for those of you following along at home. An electron volt is the amount of energy, even though it doesn't sound like energy because it's volts, but it is. It's the amount of energy that one electron will gain if it goes through 1 volt of potential difference. If you don't understand what that means, that's totally okay. The point is, it's really small. It's a tiny, tiny amount of energy. But exa electron volts, exa is 10 to the power of
18.
18. It's a 1 followed by 18 zeros. I'm not even going to try to figure out what that is in terms of millions and billions. Do you know?
Well, I guess, it depends.
It's like
It's exas.
it's like a million billion or something. Anyway, it's a lot. It's a lot. That's a lot of zeros. And so even if you take something tiny and do 10 to the 18 of them, that's a lot. That's a
Yeah.
lot of energy.
I mean, it's a lot for one particle
Yes.
to have.
Yeah, to be clear, this is not the same as, a car slamming into you or something like that. But it's a lot
Yeah.
for a particle.
I think some of the analogies I've read are things like it's about the same as a brick being dropped from your waist height to
Yeah.
hit the ground.
Yeah, or the one that I heard was it's about the same as a golf ball traveling at 75 kilometers an hour. And like a golf ball, like that's a chunk of stuff. And I now hurl that at you at 75 kilometers an hour.
No, thank you.
No, but hypothetically. And that's going to hurt, right?
Yeah.
So this is the amount of energy in one particle. Like
Yeah.
that's insane.
It's really insane.
When you look at it that way.
Because then if you do the back sums as to, well, we'll come back to what these particles actually are, but probably most of them are actually just protons.
Okay.
So singular nuclear, the nucleus of a hydrogen atom,
Yeah.
effectively,
Yeah.
right? Just a single little old proton. If you say that proton has that much energy, guess how fast it has to be traveling to have that much energy.
I can't even begin to imagine, but it would be as close to the speed of light as you can get without actually being light.
It's horrific. So the conversion actually is if you want to work out the speed, it's 0 point. Now, are you ready for this? 99999 99999 99999 99999 99951
of the
0
speed-
point. Yeah,
of
all
the
those
speed of light.
nines times the speed of light.
Holy cow. I mean, basically it's 1.
Yeah.
Yeah, it's the speed of light, which, like, those of you, again, following along at home, that's really hard to do.
Yeah.
The closer you get to the speed of light, the more energy you need to just get that little bit faster. And this is ludicrously close to the speed of light. But then again,
that was
we've already
23 nines.
identified there's a lot of energy here.
Yeah. So and this is the magic of special relativity. And I'm going to say this and drop it and just kind of leave
Drop it
it
and
there.
run, yeah.
Yeah. But if you were to experience that kind of speed,
Yep.
special relativity says that you could travel 1.5 million light years in just over 1.5 days. Well, in terms of your perception of time.
Yeah, because the whole thing about special relativity is that time and space are weird, right? And the faster you go, the more space and time changed from your perspective.
Yeah.
You know, someone else might think that 1 trillion years has passed, and you would say, no, it's just been a couple of hours, right? And that's perfectly okay in Einstein's world. And that really, really does happen. There's, in a very real sense, light, which travels at the speed of light, by definition, in a very real sense, it doesn't experience, if light could experience something, time traveling at all.
No,
it doesn't
it doesn't
experience
age.
distance at all. It's just, you know, instantaneous and over zero distance. Like the universe is bizarre that way.
Yeah.
But this one is traveling across space and time, but it's so distorted because of those high speeds and high energies that it's as if it's just a blink of the eye. It's nuts.
Yeah.
Wow. So that's exciting.
Yeah.
Do we at this point, is it worth sort of saying, okay, so this was the third biggest and it got a name.
Yeah.
So what else was up there on the podium?
So we have the second highest energy particle, same sort of thing. This one, so we, to remind you, we talked about 240 exa electron volts is Amaterasu.
Okay, so forget about the exa for a minute. Exa just really, really big.
Yep.
240.
Yep. So the second one's 280. That doesn't seem to have a name, that particle. I don't know.
It got ripped off.
Yeah, a little bit.
We should name it. I don't know, Trevor or something.
Yeah.
Keith.
Trevor Keith. Everyone loves a double barrel.
Yeah.
But the first place position, top of the podium, goes to something which I think you very casually referenced
Might have
at the
dropped
top
it
of the
in
show.
earlier. Yep.
The oh my God particle.
Yes, which has its name for the very obvious reason
Yep.
that the astronomers presumably saw it and went, oh my God, because that's insane. And how big was that?
320.
Right, so we've jumped up.
electron volts.
So 240, 280, 320.
Yeah. That was all the way back in 1991, though.
That's going back away.
Yeah.
Which also kind of points out, like, it's not like we see these every day
Well, no.
at all.
And indeed, even in our highest energy particle accelerators, so the Large Hadron Collider being, of course, the sort of super example of this. So the Large Hadron Collider gets up to 10 to the 13 electron volts, perhaps.
And this is 10 to the 18 or more. Like
Well,
it's hundreds
10 to the
of
20 if
10
you're
to the
going to go,
20.
yeah.
So that's like millions of times, tens of millions of times more energetic.
Yeah.
Which is, again, it's just nuts.
It's crazy, yeah.
Nuts. When you think of the amount of effort that we have to go through to get, you know, particles to that kind of energy in the LHC and smash them together to see what we can find inside. That's just
nuts.
bonkers. So to then have one turn up in 1991
Yep.
and then everyone go, wait, what was that? Do that again. I was like, no, the universe is not going to cooperate with that. You're just going to have to wait. And in the time since, which is how many years? Like 30 years?
Yeah. There's only
30
been
plus
two
years?
more.
There's only been two more? Like, this is not something you can prepare for. You just have to wait.
Yeah. Well, it gets quite exciting because we'll talk about, again, as already said, we'll come back to the aperture telescope. But I think I've got the numbers here that we expect to have the flux. So this is the occurrence rate of these particles above 100 exa electron volts. So the number of particles you expect to find above 100 exa electron volts is fewer than 1 per 100 years per square kilometre of detector that you have on Earth.
Okay. Another way of saying that is very rare.
Yeah.
Yeah. There's not many of these things around.
No.
But what I find interesting about that is that, like, that's a calculation which has got to be based on something. It's got to be based on, well, we would expect this many because.
Yeah.
It's like, what biggest question that comes to my mind is, why are they there at all?
Wow.
Like, I'm sure we'll get to that, but are these just, you know, you get a range of energies of particles in the universe and it's a big bell curve. You know, some of them have tiny, tiny amounts of energy. Some of them have huge amounts of energy. And these are just statistical weirdos. But even statistical weirdos, they had to come from somewhere. Like,
Yeah.
you don't just get a proton doing this without something having pushed it in the first place.
Exactly.
So,
Yeah.
yeah, we'll get there.
Right. So let's come back to actually what these things are.
Okay.
So we're talking about cosmic rays, which is actually quite confusing because we then started talking about protons, which protons are particles, but there's a cosmic ray. What is going on?
What even is that?
Yeah. So cosmic rays is a very poor word, let's say. It's a very historic word. In fact, we use rays for quite a few things that aren't actually rays in physics. It's a bit annoying.
Well, but I mean, in physics, all particles are waves and all waves are particles. An array is just, it's something that came from a direction with energy.
Yeah.
Like, it's the thing. Yeah, it's weird.
Anyway, but it comes from cosmic rays are very, very high energy particles that are observed particularly in the atmosphere. So, in fact, the ones we're talking about are, I'm gonna really muck up this pronunciation.
Do you want to spell it?
UHECR. Go on.
Oh, UHECR. No, I've got nothing. That's
ultra high energy cosmic rays.
Oh, okay, good. Yep. UHECR.
Yeah.
UHECR.
Yeah. So these are particles that are traveling, as we've said, at nearly the speed of light. We think that most of them are nuclei of atoms. So that means that they're not electrons. Some of them might be electrons, but most of them are nuclei. Right. So some arrangement of protons and neutrons. So 99% maybe of all cosmic rays are these nuclei.
And presumably, we're not talking like massive nuclei. Like you wouldn't get a uranium nucleus or something like that. But like protons or maybe alpha particles like helium. Are we thinking bigger?
Yeah, well, perhaps unsurprisingly, given the construction of the universe, most of them are hydrogen nuclei, which is
as discussed,
just a proton.
Or maybe a proton and a neutron. You can do that.
Yeah, most of this boring old protons on their own.
Right.
About 90% of them. In fact, you get a few odd helium nuclei or alpha particles.
Because that's a particularly stable way of sticking a couple of protons and a couple of neutrons together. It tends to like to do that.
But it's fractions of a percent for everything else.
Right.
So, like everything else in astronomy, it's basically hydrogen and the rest is noise.
To a rounding error, it's hydrogen, bit of helium, and everything else.
Yeah, exactly. So now these actually are quite interesting how we detect them, because you might think, well, with these particles going around the speed of light, this is going to be quite concerning. I would not want to be hit by a proton going at the speed of light. Personally.
No. Well, golf ball to the face. I mean, as we discussed. No, thank you.
Not great. So, but fortunately, we have this wonderful thing called the atmosphere that protects us from these high energy particles.
Phew.
Yes. Well, it's a combination, I guess, of the atmosphere and the magnetic field of the Earth, which is also quite helpful as well. But when it comes to the atmosphere, we don't observe these particles directly. We don't sort of stick out a detector and get whacked by this high energy proton.
Dong! What was that?
I mean, these things do.
I mean, that would be cool.
Yeah, I mean, they do hit things. Let's be clear, right? Especially above the atmosphere, lots of space satellites, the ISS, for example. These high energy particles are a problem, and they cause a sort of a background level of radiation in themselves that can be very dangerous.
Up there, you're not protected by
the
atmosphere. And so, I could imagine being rained down upon by high energy nuclei. Not good.
Yeah.
Not good.
No, so you do need shielding and protection. And, well, even it's very common even on Earth and CCD cameras to see these things sort of traipsing through your CCD. They'll So if you're, when I'm doing very long exposures, for example, when I'm working on telescopes, the CCDs are set up to detect photons. But if you get a cosmic ray, a high energy particle going through your detector, then it just basically just triggers all the pixels of the detector. You just get this light streak straight through your image.
Which is cool, but that's not what you were looking for.
No, it's a little bit annoying, to be quite honest with you. If you talk to most observational astronomers, cosmic rays are just something that they try very hard to remove out of their images rather than actually study.
I could imagine the first time that occurs, oh, look, that's a cosmic ray, that's cool. And then like the fifth time, it's like, oh, for God's sake. Like, enough, universe. I'm trying to get some work done.
Exactly. So actually, I've myself even written very substantial algorithms to get rid of them. That's part of my these very high energy particles. But when they do interact with particles in the upper atmosphere, they actually create showers. So you got high energy particle hits an atom, could be anything in the atmosphere, could be nitrogen, oxygen, whatever, and then it creates a shower of further particles from that smash up, basically.
Right, because there's a lot of energy, and so my mental image is billiard balls or pool table balls bashing into each other. But there's so much energy that it's not just that atom then rebounds and flies off in another direction. There's so much energy you can actually make stuff out of that. That collision produces new matter, which then also has lots of energy, which goes on to produce new matter. And you just get this, as you say, shower of stuff raining down on the Earth.
So we get particularly little particles called pions, called muons, and of course our favourite that we've talked about many times, the neutrinos.
Yes.
So you get these showers of, so one single cosmic ray will come and smash an atom and you get this kind of shower of lots and lots of particles. And it's actually the showers that you detect more than the actual original cosmic ray itself.
And one of the really cool, just parenthetically, one of the awesome things about this is, we see the muons from these showers, and it's like muons don't tend to pop up a lot in the world around us. We're not surrounded by muons.
No,
and
they
muons
decay quite quickly.
Yeah, they decay down into lighter things as heavy particles tend to do. But a muon it's like an electron but bigger. It's got all the same properties of an electron. It's just a bigger cousin thereof. And we don't really know why the universe decides to copy itself that way. It just does. But we don't see muons around us terribly much down here. But we do see them from cosmic rays. And the weird thing is, we shouldn't see them from cosmic rays because they get, produced in these collisions way up in the top of the atmosphere. And they should decay really, really quickly and never reach the ground. But they do because of special relativity. That they've got so much energy and they're traveling so quickly that even though that distance should not be possible for them in the time it takes them to decay, they're going so quickly that the distance to them is much, much shorter. And so they can cover that distance because of special relativity, because to them it's like it's just down there, which is really cool.
It's
a
cool.
really beautiful proof that special relativity is actually true.
Yeah.
Anyway.
I know, it's really nice. And it actually tells us a little bit about where we should put our detectors, because we want to have them low enough, and we don't want to put them right up on, we don't want to put them on satellites because you're not going to get the particle showers from the satellites above the Earth's
unless there's
atmosphere.
any backscatter or something. But I mean, that's not how these things work.
No, so we don't want to put them in space. We want to put them low enough so that the particles have a time to develop, so that the incoming cosmic ray smashes into something and you actually get enough time for those particles to actually form.
Right, so you don't want them up on the top of the highest mountains?
No. But equally, you don't want them so low that the muons and so on have all decayed by the time they can reach the ground.
Oh, right. So you want them right in the middle where you're going to be able to actually see the shower.
Yeah. So there's a sweet spot or some kind of Goldilocks zone where it's not too high and not too low. And one of those places is in the middle of the desert in Utah.
Awesome.
Yeah.
Which happens to be where this story is set.
Exactly. So around about 1,200 meters of altitude, which isn't particularly...
It's not hugely high, but it's not sea level either.
No, it's a comfortable living height.
Yeah.
I mean, you're not going to get altitude sickness or anything from that.
So what does this observatory, what does this instrument look like?
Well, this is quite cool. I didn't actually know much about this telescope before I started reading about it, so I'm quite excited. So it's an aperture telescope, and what that means is that you've got lots and lots of different detectors over a very, very large area. And if you remember when we said that you were only expecting to find one particle every 100 years per square kilometre of detector that you put on the ground.
Yeah, that's these really, really high energy ones.
Yeah. So if you put down a detector that was 1 square kilometre, you would expect to have to wait 100 years before you were certain to find a particle.
That would be a difficult one to get through the funding committee.
Yeah, that would be quite annoying.
Yeah.
And probably a very long PhD.
Yes.
So what do you do to get around that?
You make it bigger?
Yeah, exactly. So this is a detector that currently is set up to be around about 700 square kilometres.
Wow. So that's like a rectangle, which is what, 70 by 10 kilometres. That's really, really big.
It's
I don't know
really
how big the
big.
square is, but it'd be like 50 by 50 or something.
Yeah. But you don't have to cover every single square metre. You just have to have detectors that are well placed, or that are well spaced, so that you can observe. You can cover the full area without having to cover every single square centimetre.
So it's not like you need to make it this enormous dish across the entire desert, but rather as long as you've got enough coverage. So how far apart spread are these things?
They're actually quite far. They're about 1.2 kilometres.
Wow. Okay.
So there's something like 500 or so surface detectors And each one's spaced by about 1.2 kilometers out in the desert.
It's wild that can
not too
work.
bad.
Like, your mental image of this sort of says, but surely they're all the bits of the shower are just going to pass through the gaps. But I'm guessing that people have done the calculations and gone, no, trust me, this will work.
It's a bit like, so we're used to thinking about optical light, but that's because optical light has a wavelength that's very, very short, right? So we need to have shiny dishes to collect optical light. But when you go to radio light's like meters.
Yeah.
So you can just have like chicken wire and that will catch a radio wave because its wavelength is meters long. It's a bit like that.
Yeah, well, I mean, it's on a different scale, and this comes up. I this is one of my favorite analogies, so I like doing it. It's like the screen door on your microwave, right? The microwave oven. It's got this screen door on it that lets the visible light through, so that you can see what's cooking inside. But the microwaves don't know that those holes are there.
No.
Right? They're on a wavelength where, as far as they're concerned, that metal grill is completely solid. Radio waves looking at a series of antennas just see one big mirror. They don't see all the gaps. And presumably this is working the same way.
Yeah.
Right.
Basically. So there's the ground-based surface stations. There's also got three kind of which are triangulated, what they call fluorescent stations. And they're looking at the three-dimensional part. So they're looking at the ground up so that you're getting a three-dimensional view of the particles coming in, because one particle shower will hit multiple detectors. But if you want to backtrack to where it was in the sky, then you need to have sort of quite a lot of information. You can reconstruct it from the ground alone, but it's a little bit easier if you've got that third dimension already.
Well, yeah, because that's the other thing
going through.
Like that's the other thing here, right? Is it's not just wow, there was a thing, which is interesting enough in itself. One, I can imagine that you would look at all of the different detectors going off and go, okay, we can figure out how much energy there was by working backwards. Like all of this stuff hit the ground, therefore up there in the atmosphere, it must have been this, which is huge, fantastic. But then you've got to say, can we figure out where, like what direction? And that's much more information.
Yeah.
That's much trickier.
Yeah. So there's a lot of particle detectors that do this in various different ways. I don't know if we've actually talked a lot about IceCube
I remember
Super
it coming up.
Kamikande.
Yeah, but I don't know that we talked
So
in
there's
detail.
a neutrino detectors, and they do it
should.
in 3 dimensions again. So you put, in terms of IceCube, you have detectors which are on strings which go down into the ice so that you can detect in 3 dimensions where the muons are coming from. And similar with Super Kamikande, is it's kind of a big tank, and you can see all the different 3 dimensions all through.
Which
the
is
tank.
also such an awesome name.
Yeah.
Super Kamikande it sounds like something from a manga comic or something.
Well, indeed, yeah, it's awesome. But yeah, so same idea. You need to be able to backtrack to be able to say, well, where in the sky roughly did this thing come from? Now, it turns out that the fluorescent stations, they're good. They're very good when they work.
These are the ones that are trying to help determine the direction.
Yeah. But the thing with how fluorescence works is that it has to be kind of perfect conditions. And it turns out that on the night that this particular event was detected, it was a really bright moon, and you can't run the
Rats.
stations in the bright moon time. So
okay.
in this case, we didn't have that third dimension directly available. We had to sort of use some other tips and tricks with the detectors on the ground to be able to backtrack.
Hence, it's taken 2 years for this new paper to come out that says, so we figured out where it came from.
Yeah.
So how did they do it?
Yeah, well, you can still do it based on the geometry of when the particles are hitting the detectors. There's a really nice animation, which I think we'll put in the show notes, which shows the progression of the particle showers hitting the detectors, and you can see this kind of line go across the whole array. And
the timing is accurate enough that you can go that one before that one before that one. Therefore, working all of that out across a 2-dimensional array, that tells you it came from that direction in the sky.
Yeah.
Which is very clever.
It's very
and
clever.
really good electronics.
Oh, it's really hard. I can't even tell you how hard it is, because each of those substations are connected by GPS to get their timings correct. Time, it turns out, it's so trivial, but it's honestly one of the hardest things to measure. It sounds so bizarre.
Yeah, because it's not, as you just said, like you need the GPS and really, really accurate, because it's not just when did this one go off, but also, but are you sure that you know when that one went off? Like, how accurately do you know that those things have been synchronized in different places? Like, that's really hard.
And you were talking about very, very tiny fractions of seconds difference, which make a huge difference to when you do the calculations. I mean, time is awful. Time's
the worst.
It is the worst. I mean, how we define time as humans is already rubbish. But there's no particularly better way. But it's just a really hard problem to solve. But anyway, so once you've got that information of it, hit this one, then this one, then this one, and you can backtrack and then create kind of a backwards facing vector, draw a line. Where was that in the sky?
Point up to the sky. And so we've done all this work, right? Okay, so let's just, at this point, let's take stock, right? In 2021, the third highest energy by only a small margin. So let's basically say, the most energetic particle, individual thing that we have ever seen hit the Earth's atmosphere. Pow! Made a shower of stuff that rained down. Fortunately, I mean, I'm guessing these things are happening all the time. We just don't see them. But this one we did see. And over a couple of years, because it was a full moon and we didn't get the data on the day, but they were able to work backwards and go, okay, we know where this thing came from. We've got a backwards vector up into the sky pointing where it came from. We now know that it came from... And what did they find?
Well, it came from a void.
Right. And when you say a void, like the sky is dark. But we're not talking like the sky is dark. We're not talking about there are some stars and there are some not stars. What do you mean when you say a void?
All right. So we're talking now on the scale of galaxies. So this is an event that there is nothing in our galaxy that could possibly be energetic enough to cause a particle of this high energy. Right. So let's get that out of the way first.
Okay. So when we're looking up at the sky, the first thing we do is just ignore all of the stars. They're irrelevant. That's us, our galaxy. Get rid of all of those. Okay. So the next level out then is galaxies, other galaxies. Yeah.
And so galaxies tend to form structures. They form groups and clusters. So we're in a group of galaxies called the local group. We're actually one of the major players. It's nice to know.
Check us out.
I know. Yeah. The Milky Way galaxy is one of the major players.
I mean, we would say that. I don't know if the other galaxies would agree. But
there's kind of a bigger galaxy than us, but we're the second biggest.
We're there too. Yeah. We're cool too.
Galaxy, and what we call the local group of galaxies.
Yay
so depending on how you want to do the counting, it's somewhere between a 50 and 100 galaxies in our group. But then that's kind of a little bit misleading if you just think of 50 like giant, beautiful, big spiral galaxies.
It's not that?
No.
Okay.
It's us, Andromeda, and lots of tiny little things.
Okay. All right. But the other ones are cool too. We like them. They're on for the ride. It's like a gang. It's like a little gang.
Yeah, it's almost like there's two like pop stars and they've each got their own little... Because, so Andromeda has its own little entourage of tiny galaxies. We've got our own little entourage and we're kind of maybe in a duo.
Yeah. And then there's a bunch of galaxies who their job is to like fill the bowl with the brown M&Ms, that kind of thing.
Yeah.
That's cool.
Yeah.
Okay.
Yeah. So that's our local group of galaxies. We are a part of a bigger structure of galaxies called a cluster or a supercluster. And so that there's that group, and then the supercluster is kind of more on the order of a few thousand galaxies.
Right.
But we've got our little group, and then right next to our little group, we call the local group, very unimaginatively. So right next door to the local group is the local void.
Okay.
Because matter is not uniformly distributed. Galaxies are not uniformly distributed in the universe.
Yeah, it's like, this is kind of wild, right? Like when you map everything out, you get this amazing structure throughout the large-scale universe, don't you? Like things are sort of spread out along like threads and stuff.
I think the best way I imagine it is sponge.
Sponge.
Yeah, or maybe not so much Swiss cheese, because that's a bit too much solid.
There's a lot of cheese and not so much whole in Swiss cheese.
It's more sponge.
Okay, they're sort of membraney.
Yeah. So you get these what we call filaments, so long, sort of flat, sort of sheety bits, and voids. And so we understand the structure to be ultimately have formed from the underlying pattern of how dark matter populated the universe in the early part of the universe. But what we actually visibly see is that, galaxies tend to be in groups and clusters along filaments and voids, and then filaments and strands, and then there's these big holes, if you like, where there's not much.
Right. And when you say not much, like void has a kind of a chilling sense on this. Like
It does.
you just start thinking about the scale of this, like even trying to think about the scale of a galaxy. But now we're talking about like 50 galaxies in our local group, and then we're part of a much larger, call it 1,000 galaxy cluster or supercluster. That's enormous, right? So the void itself must be very big and empty.
Very, very large. We don't know exactly how large. It's quite a difficult thing to, first of all, define and then of all to measure.
How do you measure a very large nothing?
But
it's got to be very difficult.
we can put some limits on it. It's at least 150 million light years across, but probably at least 2 or 3 times bigger than that.
Yeah.
Maybe even 6 times bigger than that.
And how empty? Like really empty? Like,
Quite empty.
Quite empty.
Yeah, so it's not totally empty. I mean, there's some dwarf galaxies that roam around in these voids.
Right.
Most of the dwarf galaxies are on the edges of voids, because the way things work in the universe is that the dominating thing that's defining the position and the orientations of galaxies here is gravity. And gravity is based on mass. So if you've got mass, then you're gravitationally attracted to other things that have mass.
That's how it works.
So if you put an object in a void, there's mass that is not in the void, so it's going to be
right.
Therefore, the force is going to attract you to move out of the void.
It's not going to want to stay in the void, is what you're saying. It'll tend to. I'm going to go and hang out with these guys over here because that's what gravity does.
Yeah.
Right.
So the matter's coming together broadly in the universe. We'll put aside ideas of dark energy and
sure.
things.
Let's just park that for a minute because it's too hard.
On these scales, matter's coming together. Therefore, voids are getting bigger because the matter's moving closer. So
right, that makes sense. Yeah. Anything that was in the void wants to not be in the void anymore.
Yeah. So we can measure. There's been a few discoveries. I think of maybe on the order of half a dozen galaxies that are in this void.
Mm-hmm.
I was looking at actually the positions of these and how they map to on the sky. With if you want to see where there's you can't see it because it's void. But if you want to get a perspective on how big this void is in terms of the night sky, I was looking at the constellations. So at the moment in the northern hemisphere, then we're seeing in the early evening, we're seeing just skimming the kind of southern horizon. We're seeing constellations of Pisces and Aquarius. They're kind of just on the southern horizon. On the northern horizon, just skimming the northern horizon, is Draco. Basically, that whole space from Draco all the way across the sky to Pisces and Aquarius is part of the void.
That's a lot.
And actually a bit more because it goes below the horizon into Sagittarius.
Like that really begins to break your brain because once you erase all of the stars and say that we're not talking about that. That's a whole layer of the cosmos that we're just not interested in. So turn all those off.
Yeah.
Then you're thinking about the sky in this ridiculous distant scale. And the thought of that whole area being, that bit is empty.
Yeah.
Or at least in our relatively local area, that bit's empty.
Yeah.
That hurts.
Yeah.
It begins to hurt your brain.
It does.
The bottom line is that's a big empty space.
Yeah.
And coming back to the story at hand, that's where this came from.
Well, yes. And so
this particle, this really stupidly energetic particle came from a big empty space.
Yeah. So what could be in that big empty space that could create a particle this energetic?
Maybe we need to just, for a minute, hypothesize on what sort of thing could conceivably create a particle this energetic. Because my understanding is this is not normal.
No.
This is well and truly, this is a number of standard deviations away from what you would normally expect to see, even from the biggest booms that we see. So where could it have come from?
Well, it turns out you need a Zevatron.
Sorry?
Yeah.
A what?
Zevatron.
A Zevatron.
You need a Zevatron.
Right.
So.
I have literally never heard this word before. So a Zevatron. Go on then.
Yeah.
What's a Zevatron?
Well, you've heard of a cyclotron.
I have heard of a cyclotron. It's a particle accelerator that sends particles around in circles and either eventually smashes them into each other or sends them off towards a target to do something interesting. Yep.
Yeah. So, yeah, exactly. So a cyclotron is something that will basically give all this energy to particles and then send them off on their merry way with this lots of energy. Now, there's been a couple of particle accelerators, Fermilab, and I think there's another one that I can't remember off the top of my head, that have kind of aggrandized their cyclotrons by giving them extra Greek prefixes.
Oh, okay. Right.
So at Berkeley National Lab, they have a very large cyclotron, and they started talking about the Bevatron.
Bevatron, yeah.
Because you're getting up into these higher energies.
Oh, okay. So BeV would be what, billions of electron volts?
Yep.
Yep, okay.
And then Fermilab's Tevatron.
Tevatron, so that'd be tera electron volts, which is like a trillion or something, or quadrillion or something stupidly big.
And therefore, if you get to zeta electron volts,
You've got a Zevatron.
Yeah.
And a zeta electron volt is
10
how many?
to the 21.
What?
Yeah.
That's a lot of electron volts. Okay, but that's not a real thing, right? That we don't have one of those.
We don't have one
on
of those.
Earth, 'cause
But it
that
turns
would
out the
be-
universe must do.
Right. Okay. So this is just the scientists going, okay, how big a cyclotron or equivalent process would you need in order to make this? And the answer is it's a Zevatron. It's that big.
Yep.
We couldn't do one here, but what could? Like, giving it a name is one thing, and
Yeah.
that's cool. Great, we have a name to throw at it. And let's be honest, astronomy hasn't been great at naming over the years in many fields. So
No, it's on and off, isn't it?
I applaud their efforts on this one.
Yeah.
Like, well done. But what is this? What has happened here?
So, I mean, we instantly, as we say, rule out anything that could be in our galaxy.
Right.
Even take the most energetic supernova that you can possibly imagine.
No,
not
like,
even going to touch.
not even close.
Yeah.
Okay.
No. So we need to go out to some of the most energetic events in the universe. These are things like supermassive black holes, active galactic nuclei, maybe mergers of very, very compact objects. I mean,
Like black hole mergers or neutron star mergers.
Yep.
Like, these things are stupidly energetic.
Yep.
Sure. Could that be enough? Like, could it?
well, even those, I think it's pretty, difficult to get up to these energies. I think the closest we can get with modeling is the most energetic active galactic nuclei that we've seen, and that's only under very specific circumstances. But active galactic nuclei, which are these feeding supermassive black holes, turns out they you can kind of see them.
Yeah.
They've got other signatures.
Yeah, I mean that's kind of the thing, isn't it? Is that anything, like, surely anything which is capable of throwing out a proton with this amount of energy,
Yeah.
would be throwing out other stuff that we could see too.
Yeah, and let's be
like,
clear,
it's
this-
not just going to go and I'm done. Like, that's not going to happen.
No,
So
there'd be
it
all
shouldn't be
sorts
coming
of
from a
stuff.
void, right?
And this is a local void. Like, this is right next door to us.
So
Right?
this should be the easy one.
Yeah, this is not, I mean, all the other active galactic nuclei that we study, we're talking about really far away, right? And other clusters and other groups of galaxies, not in the little local, neighborhood.
Is there a chance, like, the void doesn't go on forever, right? It's a bubble.
Yep.
So there's stuff on the other side of the void, right? Like, did it come all the way through the void?
Well,
Is that possible?
you would imagine so.
Yeah.
Turns out that no.
Oh,
Because the
I
problem...
thought I just solved the problem there.
Yeah, I know. It's a good answer.
Thanks.
But we've got this problem called the cosmic microwave background.
Yeah.
And so if you generate an insanely high energy particle, yes, it will travel through space, but it can't travel through infinite space unheeded without losing energy.
Right, because the cosmic microwave background, so this is the wash of energy across the universe, which is basically the same everywhere to within tiny changes, right? But this is left over from the Big Bang. This is the last glow from the Big Bang when all of the matter in the universe, things cooled down enough that things were able to form atoms. And the universe suddenly became transparent to light, and it just whoosh, off through the universe. And it's a snapshot of that point in time. Point is, it's everywhere. There is this radiation everywhere in the universe. And even though there's not much of it, you're still traveling through it, and that's going to be just a continual interaction for this proton as it's going through huge distances of space.
Yeah.
And so it's going to lose energy.
Yeah.
Right.
So the furthest away that this particle could have come was about 160 million light years.
Which is kind of the scale that you were talking about of the bubble.
So it has to have come from in the void.
So it had to come from the void. Oh, but no, because it can't, because we'd see it. Like,
There's just nothing. There's only these pathetic little dwarf galaxies just sort of mooching around.
Are you about to tell me that we have no resolution to this problem right now?
This is honestly one of the papers that has been the most honest in saying, yep, we've got
have
no
no
idea
idea.
what's going on here.
I mean, that's cool, right? That is awesome because it genuinely is like, that's a mystery.
It is a mystery.
That's a huge Scooby-Doo style mystery of what just happened.
Yeah.
Okay, so first of all, is it possible that they got the direction wrong? Like how, like what's the error bar on that vector pointing up into space?
Well, yeah, not enough.
It's like, it's a big void, right? It's not like, oh no,
yeah.
hang on, sorry, we meant that pulsar next door. No, it's a big void.
Yeah.
So no, okay.
So there's kind of three conventional potential explanations.
Okay.
None of them I would say particularly good, but
Yeah.
they're at least conventional within our
Three is
understanding
three
of
is kind of
physics.
one of those numbers that you come up with. It's like, we need to say something. Quick, come up with like, what have you got? Okay, good. I'll write that down. Okay,
Yeah.
you, any ideas? Good. We need a third, right, to cover our bases.
Yeah.
So, okay, what are they?
So the first one is, so maybe the magnetic fields, the local magnetic fields between us and this local void are bigger than we thought.
Because magnetic fields can accelerate charges.
Yeah.
So,
And they change the direction, particularly of charged particles, right?
oh, I see. Right. So it's not necessarily that the magnetic fields would have created the energetic particle, but rather the energetic particle was created somewhere much more obvious. Like, oh, that thing over there, but then it's been bent.
Yeah.
Right. To make it look like it's coming from the void.
Yeah.
Okay. So, all right. You're not looking convinced.
Well, you've got to have some pretty strong magnetic fields. We don't really have any evidence for those. And then you still got to have a source.
yeah.
Even if
I
it's
mean,
not where it's not in the void, which
Yeah.
has obviously got nothing in it. But
yeah, this doesn't help us to identify the source. It just says maybe the source is somewhere else.
Yeah.
And they would have to be pretty intense magnetic fields because this thing's traveling really, really fast.
exactly.
Okay.
So, I mean, maybe.
Sure.
Option number 2, it's a source that we don't know anything about, an unknown source.
Well, that's kind of the lift up the carpet and sweep it under there with the dark energy and the dark matter. Sort of,
Maybe we should have just added it to that problem.
yeah,
It's obviously dark matter.
and it's dark sources now, dark, ridiculously energetic.
Well, maybe
things.
that is it's a dark source.
It could be.
You've just coined it.
Yeah,
Go for
HP.
it. The third option, our understanding of particle physics is incomplete.
Again, that's the sort of theoretical version of lift up the carpet and put it in there with the dark matter and the dark energy. Maybe it's something that we've never seen before, or maybe it's something we've never thought of before.
Yep.
Good work, everyone.
Yeah, well
Great.
done. Do you want the unconventional theory that I
Yes,
did read?
please.
'Cause
Yes, please.
This one's very exciting.
Because those three are not particularly convincing at this point.
Well, maybe there are some defects in space-time that mean that this has actually come through a completely different part of the universe, through a cosmic string wormhole. Who knows?
Okay.
And it's just appeared here.
I mean, that sounds awesome. Again, sure, why not? Let's just invent science fiction now and throw that one in. And in comparison to the other explanations, it's probably got as much predictive power. So, what you're basically saying, Emily, is we have no idea.
Exactly.
Good. Excellent. Job well done. Well, Emily, look, coming out of this particular story of modern astronomical research, all I can think of is that this is quite possibly the slowest experiment I've ever heard of in my life. That, we just have to wait an undefined and indeterminable period of time for the next one of these to come along, and we can add another data point to the 3 we currently have. And slowly but surely, maybe we'll be able to figure out what the hell's going on.
But this situation's rather common, really, in astronomy, right?
Right.
We do this all the time. We're used to knowing it, well, wanting to understand very, very rare events in the universe. And what do we do when there's very, very rare events? We just look at massive chunks of the sky and just wait for them to roll on in.
Yeah. Although, again, I kind of feel like this would be a very difficult one to get past the funding committee. Is we just need to build more of these really, 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 really big, strange telescopes covering the desert in the hope that we see another one. How many of these things have you seen so far? 3. Like, I can't see it getting up, you know?
How many Higgs bosons did you see?
Well, fair point. Well, actually, in the end, like, quite a few, just buried in ridiculous amounts of statistics, I guess is the point.
Yeah.
But your point is well taken. Yeah. You know, you can probably buy a lot of these antennas with one Large Hadron Collider. But look, we'll leave the arguments between the particle physicists and the astronomers for another time. Emily, if people wanted to get in touch with us and weigh in on their particular pet theory on where the hell these 3 particles have come from in the universe, how could they do so?
Well, first of all, you should head over to syzygy.fm.
Yes, indeed.
Because there's a really rather lovely contact us form, which you can fill out and you can write about all the things that you think we should be covering in this podcast. And turns out we often, nearly always, turn those into full episodes.
That's right. We've done a number of those over the years. We've probably done half a dozen or more of those over the course of Syzygy. So write to us and tell us what you think. Give us feedback. Tell us what you love and what you don't love. Give us ideas. But we're also on the interwebs. We're on the social medias. We are on Instagram at SyzygyPod. And because Instagram kind of throws in its new Twitter version, Threads, for free, we're also on there too.
Yes,
so,
still no idea what that is.
You should go and check it out. It's basically Twitter, but done by Meta. So it's Meta Twitter. I don't know. It's very confusing. But yes, we're on there at SyzygyPod. We're also on Facebook. And you go and find us on Facebook by doing the thing on Facebook that you do, which is just finding us. Just put in the search thing. It's just not hard.
SYZYGY.
That's right. That's all you've got to remember. If you want to support the show, first of all, tell everyone you know that it's a fantastic podcast that talks about bizarre things in the cosmos. And if you know someone that you think would be excited by that, share the love around. That's the best thing you can do. But if you want to support us financially, head over to patreon.com/syzygypod, where you can sign up to throw us a pound, a couple of pounds, a couple of dollars a month and help us to keep the electrons flowing through the website and to help us do the things that we do. But otherwise, Emily, look, I don't know whether or not we're going to be able to crowbar in another episode before Christmas. We'll have to see. I'm heading off to Australia in a little bit over a week, which is exciting.
It's rather nice.
Yeah, first Australian Christmas in the best part of a decade. So that'll be cool. So we'll see what we can do. But if not, I guess we'll talk again in 2024, which is crazy.
That's too far in the future. We'll all be running around with Zevatrons by that point.
Zevatron for everyone for Christmas. Anyway, if I don't speak to you before, have a great Christmas and New Year, everyone.
We'll see you
in
fabulous holiday season.
2024. Bye.
Bye.